All right, what's going on, y'all? We got 348, another symmetry problem. They give us E and A for every element, and we have to use symmetry to determine displacements of the nodes and the stresses in each element. So this problem is pretty long, but I go into full detail, so you shouldn't have any questions. And if these problems help you guys, let me know. I'm just like, maybe I'm not explaining something right. If I'm not, just let me know, or just like anything, you know what I'm saying? I don't care about likes, I don't care about subscribers. Just like, let me know if this helped you. If not, that means I got to change something up, because at the end of the day, these videos are for my sister, and if she doesn't get them, well, if you guys don't get them, she's not going to get them. You know what I'm saying? So just anything helps, but you know what? Let's go ahead and get started. All right, guys, so another symmetry problem, but before we start filling in this table like we always do, right, first let's kind of analyze what it is we're dealing with. So it is symmetrical. So about the y-axis, you notice there's two pins on each side. They're all the same properties of, it's the same property, modulus is E210, whatever. Cross-sectional area is all the same, 10 times, well, it's 10 to the negative 3, right? Just, I don't know why they did that. I guess that's cool. But it's 10 to the negative 3 for your cross-sectional area. We have 20,000 going down here, and then one down in the middle. So you want to split this model just using the left side, right? So if you do that, you're going to have this little piece right here. And the assumptions you make, pretty important, right? When you do this, you're going to assume that there's no translation in the x direction for these two nodes right here. So that's a real important assumption you have to know how to make. If not, you're going to have trouble with this problem. There is theory behind it, right? But point is, like, I'm not sure if you watched, I think it was 332 or maybe even 320, something like that I did. It was a couple months ago, maybe a month or two ago. The nodes here, they do displace, but very little. I think in the other problems we got like 1/3 of a millimeter, and that's really, really small. So this assumption is safe to make, right? We have another pin right here that's already given. So check it out. This pin right here is preventing translation in the y direction, so that means V1 is 0. This one's preventing translation in the x direction, so that means U3, right? That's node 3, and 4 are 0. So using these boundary conditions, we could solve the problem. We're gonna have 5 unknowns, right? We have 1, 2, 3, 4. Well, actually, you know what? I can't remember. I think it was 5 unknowns. Yeah. So it's there's 8 unknowns total, right? X, Y direction for every node. And then we already got rid of 3 boundary conditions where these 3 are 0. So that means there's 5 unknowns left. So it's solvable. We're gonna use a calculator. I'm not gonna solve for those, but you know what, let's kind of just keep going. Okay, so before we fill in this table again, we need to get lengths as well. We're gonna need it for EA over L. So the length of one, okay, so before we get the length of one, just real quick, this is 8 meters, it goes up 4 meters, and by is an 8 meter right here, 4 meter going up, that means this is 8.94. That's just trigonometry. Something else that they don't tell you, it took me a while to understand. Apparently this is halfway, okay? I'm not sure, maybe during an exam, ask your professor if that's exactly halfway, but apparently it is. I guess that's something you should know, but they really don't give us any clues. At least I don't see any, all right? But just FYI. So 8.94 divided by 2, that's going to give us this length and this length. That's 4.47 and 4.47 right here. Length 3 is the same. This is a perfect, what do they call it? Those triangles that are the same angle here, same angle here. I forgot what it's called, right? I think it's a scalene. There we go. But point is, L3 is also 4.47 in length. L2, they give it to us. It's this one right here, 8 meters. And then L5, it's 4 meters going up and down. All right, so now that we got that, we got to fill in the stiffness matrix for each element. And to do that, we need all these values, C squared, S squared, and CS, right? EA over L, we're going to need it to fill in the little matrices for each element. The angle, so the angle is really important. I covered it in the previous video, problem 346. Check it out on the channel if you haven't seen it, but I go really into detail on how to do it. I'm only going to do it for one element here. I did it for all the other elements in the other problem, but in this one, just to save time, I'm not gonna do each one, but I'm gonna do the most important one. So check it out. Element 1 is this one right here. It goes from nodes 1 to 2. I like to start from the smallest to the biggest. So 1 to 2. That angle is gonna be this angle right here. We know from trigonometry, that's gonna be angle 26.58 degrees right here. Okay, so that's gonna be 26.58 degrees. Fill in the cosine signs. That's going to be 0.89. That's going to be 0.45. That's going to be 0.79. 0.20. 0.4. And that's it. Okay, we'll do this one later. Element 2 is this one right here. It goes from 1 to 4. That angle is 0 degrees. Do the cosine signs. All right. Okay, that one was easy. Element 3. That one goes from 2 to 4. I always go from smallest to biggest, okay? 2 to 4. That's going to be angle 333.42 degrees. Now, I'm going to show you how to do this one. So these were pretty simple. You'll understand how to get these if I show you how to get this one. So again, I like to start from the smallest node, right? So I went from 2 to 4. That means my axis or datum reference is right here, right? This is the origin of your plane. And I go from here all the way here. That's 180, 270. And then because of trigonometry, I know this little angle right here. Now, I don't know off the top of my head, right? I gotta pull it up. So let's see. If it's 333.42 minus 270, that angle's 63.42. This little angle right here, I'm gonna draw theta. This little angle, that's 63.42. And there's theory behind it, right? Because look, we know this angle. We just said it was 26.58. If you draw a straight line down, it's well, you know, 180 degrees makes up a triangle. So we know this angle. This is 90. 180 minus both of these, that's going to give you this one right here. And then this little angle is also going to be 26.58, reaching up to the top. That's how you do it, okay? So I start at the smallest node and I go to the biggest. So I do the turn, you get me, all the way around. You could have also done negative 26.58. It's the same thing. I just like to keep angles positive just to avoid confusion. But that is how you get the angle. So now you can imagine for element 1, we went from 1 to 2, so our axis was right here, and it went up 26.58. For element 2, it went from 1 to 4, and it stayed at 0 degrees. That's all it is. So that, just a FYI, that is how we get the angles. I cover it more in depth. If you want to see problem 346, feel free, but just wanted to give you a heads up. That's how you do that. So this is 0.89 when you take the cosine. This is negative 0.45. This is 0.79, 0.2, and negative 0.4. Element 4 goes from 2 to 3. That angle is going to be, okay, 2 to 3. That angle is going to be 26.58. And yeah, get the cosine signs, 0.89, 0.45, 0.79, 0.2, 0.4. Element 5, finally, it goes from 3 to 4, so I'm going to use angle 270, okay? I have my origin here. I'm going to go all the way around to 4. It's 270. And it's real important, and this is really important, okay? It goes from what node to what node. Again, if you've seen my other videos, you know why it's important. I'll say it again, just give me a second. Fill this table in, 0, negative 1, 0, 1, 0. And, well, when I get there, I'll explain it, okay? EA over L. So this is another really important part to symmetry problems, okay? EA over L is normal for every element except the one you're cutting in half, okay? So EA over L for the first element, EA divided by L. That's going to give you 4.7 times 10 to the 7, okay? Make sure you know how to get these numbers. That's just math, basic math, right? Okay, element 2, EA divided by L, 8. That's 2.62 times 10 to the 7. Next one, EA divided by L3. That's for the third element. That's going to be another 4.7 times 10 to the 7. And then similarly for element 4, same length. So it's going to be 4.7 times 10 to the 7. And then finally, element 5. So the area gets cut in half. That's going to be 10 to the negative 3 over 2. and then the force also gets cut in half, remember. So that 20,000 becomes 10,000. F of 3 to 4, area of 3 to 4. Okay, these are two important realizations you have to make. I don't know, right? The point is, it normally would have been EA over L, 4, and that would have given you like 5.25, I think, or something like that. But because we cut that in half, now it's 2.63 times 10 to the 7. It's really important. That will mess you up if you don't do that, okay? So just always remember, for the one you're cutting in half, you got to cut that in half too, the EA over L. All right, that means we could go ahead and fill in the matrices for each element. K1, the stiffness is EA over L. We're following this formula right here, okay? So that's 4.7 times 10 to the 7. Let me go ahead and do that. That one goes from nodes 1 to 2. So you're going to have U1, V1, U2, V2. Now, if you would have went from 2 to 1, your angle would have been this angle, whatever that is, right? I don't feel like doing it. And then you would have had U2, V2, U1, V1, okay? Just FYI. But that's why I always like to just go from smallest to biggest. It's more, I don't even know, but it's just my style, you know. Guess you could have your style. But yeah, that's that one, okay? Now let's go to the next one. Let's see, K2. We got 2.62 times 10 to the 7, right? That one, it goes from nodes 1 to 4. So we got U1, V1, U4, V4. Then similarly, U1, V1, U4, V4. Okay? All right. What else we got? What else we got? Next one. So we got K3. K3 is actually, you know what? Yeah, 2.62, my bad. K3 is 4.7 times 10 to the 7. So we got 4.7 times 10 to the 7. That one goes from 2 to 4. So U2, V2, U4, V4. Same thing across. U2, V2, U4, V4. Okay. K4 now. Let's go ahead and do that one. That one has a stiffness of 4.7 also, times 10 to the 7. 4.7 times 10 to the 7. That one goes from nodes 2 to 3. So U2, V2, U3, V3. And then it, same across, right? U2, V2, U3, V3. All right, finally K5. That's going to be a stiffness value of 2.63 times 10 to the 7. And that's going to go from nodes 3 to 4. So we're going to have U3, V3, U4, V4. Okay. Similarly across U3, V3, U4, V4. Awesome, awesome, awesome. It's looking good. It's looking good. All right, now we're going to use the cosine squared, sine squared, and cosine sine values for each element, right? We got them right here, these three columns. Boom. For each element, it's going to change, obviously. So for the first element, we're concerned with 0.79, 0.2, and 0.4. And it goes diagonally across. But before we start doing that, let's go ahead and apply the boundary conditions. It's going to save us a lot of writing. And, well, yeah, so you know V1 is 0. So everywhere you see a V1, cross out the column and the row. So that's gone right there, okay? There's another V1 right here. All right, it's looking good, looking good. There's no more V1s. That's it, cool. U3. Anywhere you see a U3, it's gone. There's one right here. And, okay, that one. Oh, shit. Yeah, let me erase it. I don't like it. Came out a little too crazy right there. Went a little too fast. All right. Whatever. Shit, that one came out uglier. But U3 is gone as well here. Okay, off to a good start, And then U4 is gone. So this one's gone, and this one's gone. U4 is gone. U4 is gone, and U4 is gone. Cool. So now we could go ahead and fill in the matrices. For the first one, at position U1, we have a c squared, right? So that's going to be c squared, 0.79. We have another c squared here, right? I'm just following the matrix, okay? Just c squared here, 0.79. S squared, that's 0.2. I'm only concerned with these three for now. Then we have CS, negative CS, CS. And then, so it's that one's gone, negative CS, negative 0.4. Then U2 is negative c squared right here, so it's negative 0.79. This one's negative CS, so that's another negative 0.4. Okay. It's symmetrical, so that means negative 0.79, negative 0.4, and negative 0.4. But that just means it's the rows are columns. So CS, negative c squared, negative CS, negative CS, negative s squared, CS. It's just diagonally symmetrical. All right, so those are the numbers. K2 now, we're concerned with 1, 0, 0. So anywhere you see, this is going to be a 1, 0, 1, 0. CS is also 0, 0, 0. Cool, that one was easy. All right, next one. Right here, K3 is 0.79, 0.2. So it's 0.79, 0.2, 0.79, 0.2. Then CS was negative 0.4. So that's negative 0.4, the 0.4, then negative 0.4 also crossed out, right? Yeah. So then negative c squared, negative s squared was negative 0.2. I hope you understand what I'm doing, to try not to get mixed up with the bars. If it does mess you up, fill in the table regularly and then do the boundary conditions. It just saves you more time if you do it this way. Negative CS for element 3, negative becomes a positive right here, so 0.4. And it's symmetrical, so negative 0.4, 0.4, negative 0.2, and that's it. Next one, K4, it's 0.79. We got 0.2 and 0.2. You kind of get the hang of it, you know, c squared, s squared, c squared, s squared, CS, negative CS, CS. It's just find a pattern, and it's diagonal. So that's my way of thinking about it. 0.4 for CS, so it's going to be 0.4. That one's crossed out, this one's crossed out. Okay. Negative c squared, negative s squared, so negative c squared is crossed out, negative s squared, that is negative 0.2. Then finally negative CS, that is negative 0.4. Fill in the rest, right? 0.4, it's symmetrical, negative 0.4, negative 0.2. All right, last one, let's see. This one's K5, so the numbers are 0, 1, 0. So it's 0, 1, 0, 1. Then this is going to be crossed out. Then CS is also crossed out, okay. Then this one right here is negative s squared. What's negative 1 and negative 1? Nice. That one's a little easier. These two are easy. So, all right. So now before we add the matrices and start putting it into this matrix, we cannot do that unless they all share the same multiple on the outside of the matrix. So in this case, all of this is multiplied by 2.62. All of this is multiplied by 4.7. All of this is multiplied by 2.63. All of this, 4.7. All of this, 4.7. So let me go ahead and do that. I'm going to multiply 4.7 into everything. I'm going to erase these numbers and get the new ones. Do the same for every single matrix, and then we should be able to add them. All right, you guys, had to reposition the phone, just FYI. But I noticed I made a mistake. This was a negative 0.4 that I had put. It should have been positive, okay, just following the formula. For some reason I put negative, but it's actually this value that we had to put here. And then that one's also this one, so they changed. This was negative 0.4 that I had put. It should have been a 0.4 positive. And yeah, I did the math, so if you didn't get these numbers, double check them, but these are correct. So it's probably just FYI, like a calculator mistake that you probably did. And don't worry about rounding too much. I think 2 decimals is fine. Obviously you won't get the perfect answers, but I mean, it's normal, you know, you're not a calculator. It's not it's not that big of a deal. But so once I did that, all the numbers I was multiplying to, I erased them because now they all share 10 to the 7 on the outside. And that means that we could go ahead and just start adding them. So I'm gonna go ahead and do that here. Let's apply the boundary conditions one more time. So we know V1 is gone, we know U3 is gone, and we know U4 is gone. Then I had a straight edge here the whole time, so I didn't have to mess that one up. But we also do it across, right? V1, V1, so that's gone. U3, V3 is gone, so let me cross that one out too. And then U4, I'm sorry. If I said V3, I'm sorry, but can't remember. Literally just forgot, but those get canceled out, the rows and columns. V1, U3, and U4. All right, so let's go ahead and start adding the positions, okay? So U1, U1s, we got one right here, 3.71. What else? Let me see, I wanna make sure you can see the paper. There we go. So 3.71 right here. We got a U1 right here, 2.62, and that's it. So if you add those, you will get 6.33. Add all the U1s, U2s. So U1, U2s right here, negative 3.71. There's no other one. U1 and 4 here. Yep, that's it. So it's negative 3.71. Pretty much just look for the matrices where there's a U1 involved. So it's the first two, this one and this one. So that's going to be the whole first row. U1, V2, there's one right here, negative 1.88. There's none right there, so it's just negative 1.88. U1, V3, that's 0, there's nothing, right? And U1, V4, there's one right here, 0. Now just FYI, I'm going to let you know right now, you're doing it correctly if you get a symmetrical matrix, okay? If you don't, you might want to double check your work, just FYI. You'll see in a bit. We'll go ahead and do all the values. So let's do U2, U1. Let's do one more row and then I'll give you the rest of the answers. So node 2 comes out here and here. So these two matrices. U2, U1. None of them. 0. Well, actually, hold on. Oh, there's one more. The top matrix. Yeah. It wasn't symmetrical, which is why I knew it was a mistake. There's a U2 here too. So these three matrices. U2, U1, negative 3.71. U2, U2, that is this one, 3.71, 3.71, 3.71. That is 11.13. U2, V2, so there's a U2, V2 right here, 1.88, negative 1.88, that's 0, and then U2, V2, 1.88. So that is 1.88. U2, V3, so it only shares it once right here. U2, V3, negative 1.88. And finally, U2, V4, it's right here, 1.88. All right, so that's that. I'm gonna go ahead and give you the rest of the numbers. And if you did it correctly, this is what you should get. 11.13 is a 2.82 this way. There's a 3.57 this way. There's a 3.57 this way. There is a negative 0.94 this way. Negative 2.62. Negative 0.94. And it's symmetrical. So if you do it correctly, pretty much what I was doing for the first two rows, you will get this right here. And the matrix is symmetrical. Now, I can't say that with 100% guarantee. I wish I would have noticed it earlier, but lately, since I figured that out, I kind of noticed that, oh shit, this one's positive. I kind of noticed that that's the case. So I wish you could start doing it from the beginning too, but by the time you see this video, I'm assuming it's already too late for you to. But whatever, it's not that big of a deal. 0, 0, and then this is a negative 1.88. All right, so that's where we're at. So we're gonna go ahead and, oh, and there's a 10 to the 7 right here, okay? Don't forget that 10 to the 7, okay? And yeah, so now the boundary conditions, remember V1, U3, and U4 were 0. So that means this is 0, this is 0, and this right here is 0. So now, if you know displacement, you don't know force. And if you don't know displacement, you know force. So let me show you what I mean. At position 1, or at node 1, we don't know displacement in the x direction, so we should know the force in the x direction. There's nothing being applied. Just looking at it, there's nothing. So that means that is a 0. Okay. Okay, cool. Next one. U2. In the x direction at node 2, there is nothing being applied. In the y direction is negative 20,000, but in the x direction, nothing. So this one is also 0. Okay, position 2 for the x direction, node 2. In the y direction, there's a negative 20,000. We don't know V2, so we should know F2y, and we do, negative 20,000. Okay, negative 20,000. All right, what else? V3 and V4. So those are gone too, so that means we should know the force. And let's see what that force is. Just by observation, there's a negative 10,000. Remember, symmetrical, 10,000 in the y direction, so negative 10,000. And then at 4, there's nothing going on, so that's 0. Boom. Now let's take it a step further. Let's divide both sides of the equation, because this is F equals kx. You know, like it's a stiffness times displacement will give you a force. So if you divide both sides by 10 to the 7, this side of the equation by 10 to the 7, this side of the equation by 10 to the 7, this goes away, and you divide 10 to the 7 to all these numbers. Now the only ones that get affected are negative 20,000 and negative 10,000. Okay, so let's go ahead and populate that. If you do the calculation, you're gonna get negative 0.0, what was it, 0.2, I think it was? Yeah, 2 zeros. I already have it in the back. And then you'll get negative 0.001. And we could go ahead and start assembling the equation. So the first equation is going to look like this, just letting you know. So I'm going to flip the page. I'm not coming back. 0 is equal to 6.33 U1 minus 3.71 U2 minus 1.88 V2 plus 0 V3 plus 0 V4. Same thing for all of them. Let's do another one. Let's do the fourth one right here. Negative 0.002. Well, in this case, it's going to be 5 equations. 1, 2, 3, 4, 5. Forget these for now. F4x, F3x, F1y. The third equation, which is negative 0.002, is going to be equal to negative 1.88 U1 plus 1.88 U2 plus 2.82 V2 minus 0.94 V3 minus 0.94 V4. And that's what I got here. All right, so let me flip my page on the other side. So you know what? I'm not going to do the calculation, but if you're looking at the screen, here's a screenshot of a calculator that I found online. It's a 5x5 matrix in this case, right? We have 5 variables, U1, U2, V2, V3, and V4. And I just put them in order, right? X, Y. I forgot that. I'm not looking at the screen, but they're just alphabetical order. And when you put in the inputs, right, you should know how to do this, I'm assuming. Just put in the integers before each variable for each equation into it. Make your 5 equations, set it equal to the force vector, which is 0, 0, negative 0.002, negative 0.0001, whatever, and 0. And click calculate, and it should give you the numbers. They're pretty accurate. We're not going to write down the whole number, but I mean, to a very significant amount of digits. And yeah, these are the numbers right here. So let me go ahead and write them. U1 is equal to negative 0.002027. What else? U2 is equal to 0.00087,087. And they're all in meters, just FYI. V2 is equal to negative 0.00911351. What else? V3 is equal to, what is it? Negative 0.00938815. And the reason I didn't do the math was because if this problem does come up on the exam, your professor is not going to make you do that unless he really wants to be an ass. But I'm pretty sure he's going to let you use a calculator for all this stuff. And let me explain why it's in meters real quick, just in case you didn't know. But we got our EA over L in newtons per meter. This matrix is dimensionless. This number was 10 to the 7 Newton per meter. I converted these numbers to newtons, remember? 20,000 and 10,000, whatever. So that means this is in meters. That's the only way it makes sense. So yeah, this is the answer right here. Let's go ahead and box that in. And now we could go ahead and do the stresses. So the stresses. All right, this is the formula right here. Sigma is equal to E over L. No area included. It's per unit area, remember? It's negative cosine, negative sine, cosine, and sine of that specific element. And then that specific element's nodal direction, I guess. It starts at node 1 for a couple of them, right? And they end up at another node from whatever node. So in this case, for the first element, it's going to be U1, V1, U2, V2, right here, okay? That's all it is. So let's go ahead and do one. We got sigma 1 is equal to, it's going to be sigma from nodes 1 to 2, which is also equal for sigma from 6 to 5. So we're doing symmetry, remember? So you got to take that into account. So sigma 1 is element 1 is sigma from nodes 1 to 2, which is also from 6 to 5. That's all that is, okay? All right. If you get the E, you know what? Let me go ahead and put them right here for you. Shit. You know what? Yeah. I'll put it right here. Sigma. You know what? Not really sigma. Let's do E over L. E over L for elements 1, 3, and 4. If you do the math right, E over L for each L changes for each element. Remember, that's gonna be 46.98 times 10 to the 9. For element 2, that's gonna be 26.25 times 10 to the 9. And for element 5, remember that it is 52.5 times 10 to the 9. For EA over L, it's important to cut 5, remember? But when you do E over L, you don't do anything. The length is the same when you cut it in half, and the property E will always be the same. So that's why this is 52.5. It's treated just like E over L, just like any other case. There's nothing special about symmetry when you're doing E over L, just FYI. All right, cool. So sigma 1 is equal to E over L of the first element. So I can do this, sigma 1. It's 46.98 times 10 to the 9. The cosine and sine of that element. So that's 0.89, 0.45. 0.89, hold on, 0.45, but it's negative. So it's negative at first, and then it's positive. So 0.89, 0.45. Now, the vector is U1, V1, so it's negative 0.00222027. And V1 is 0, right? It was a boundary condition. Then U2, yeah, it goes from 1 to 2. So U2, V2 now, we got them right here. This number and this number. So that is 0.00087087 and negative 0.00911351. All right, if you do the math, I'm assuming you know how to do this by now. Sigma 1 is equal to 46.98 times 10 to the 9, open parentheses, this number times this number, plus this number times 0, plus this number times this number, plus this number times this number. So if you do the math, you'll get like 0.001962. And the more exact you are with these values, the closer you'll be to the true value. I know you don't know what the true value is, especially on the exam, right? But, you know, I mean, it doesn't hurt to just add a couple extra numbers when you do this. Add all these three terms together, multiply it to this. That means sigma 1 is equal to, what is that? Sigma 1 to 2, which is also equal to sigma from 6 to 5, which is equal to negative 64.44 megapascals. And that is in compression. Now, hold on. The reason I told you that direction of the nodes was important, let me just go ahead and show you an example real quick, okay? So you know how right here we got negative, cosine, cosine, and sine? And this determined that it was in compression, right? These signs, because negative to negative, that became positive. It's just a sign switch, okay? Let's say you would have went from 1 to 2 supposedly here on your stiffness matrix, but you went backwards here. You would have had a negative 0.89 here and a negative 0.45 here. Those negatives would have became positive here, and overall this number would have just became positive. And it would have told you it would have been in tension. That's why it's real important to determine, to stay consistent, not determine, to stay consistent with whatever direction you choose. And just follow the process that you learned here in this video and you'll be all right. Now I'm gonna go ahead and give you the rest of the sigmas. All right, so here are the numbers. I'm gonna go ahead and explain each one. I got the other paper right here, but real quick to verify this, well, you really can't verify any of them, and it's kind of hard to see it in tension or compression sometimes. I know in other videos I told you, you could always just kind of see it, but this one's kind of hard. But, you know, sigma 5, it's 19.29 megapascals. Now, the cool thing about these, for some of the problems, when they're applied in the axial direction, so in this case, right, 20,000 is applied to this beam right here, which has an area of 10 to the negative 3. If you do 20,000 divided, because it's, you know, stress is equal to force over area. So if you do that, what do you get? 20,000 divided by 10 to the negative 3. 10 to the 3 negative, you will get 20 million newtons per meter squared, which is also equal to 20 megapascals. And yeah, that's kind of what we got, right? This is just a rounding error, don't trip. But yeah, that's a cool way to verify it. Tension and compression, you might think it's in this case compression, but it doesn't always work like that directly. It's not something that you could see just visually like that either, unfortunately. But in this case, we just take your number's word for it, you know. But that's a cool way to verify real quick. Now, these are the numbers themselves, right? Sigma 1 right here, that's the one we just did. Sorry for this problem actually messed me up, it threw me off a little bit, but the numbers right there, that's the one we got. Sigma 2 goes from 1 to 4, which is also node 6 to 4, symmetry. E over L, the cosine and sine of element 2, and then obviously negative and positive, right? Or yeah, negative, negative, positive, positive. And then this is, in this case, U1, V1, U4, V4, because it's between those nodes, okay? Next one, and that's how you do the math, right? This number times that, plus this number times that, this number times that, this number times that, you'll get that. Multiply 26.25 times 10 to the 9 to it, you'll get that right here. Let's do another one, right? Sigma 3, that goes from nodes 2 to 4, which is also 5 to 4. That's the E over L. These are the cosine and sines, the negative versions of element 3, and the positive versions. And then this right here is U2, V2, U4, V4. Do the math again, just like we've been doing, right? And then you will get negative 23.44 megapascals compression. Next one, element 4, goes from 2 to 3, and symmetrical, 5 to 3. E over L, negative cosine, negative sine of element 4. It changes for each element, just FYI, remember? Every element has a different cosine and sine value. Then this is going to be U2, V2, U3, V3. And then do the math, right? And then you get that number right there. Finally, sigma 5, E over L, right, the one we got here. Cosine and sine, the negative versions and the positive version of element 5. That's U3, V3, U4, V4. Do the math, you will get 19.29 megapascals. So that's all it is. You know, it's a pretty long problem. It's a little complicated because not all the numbers are kind of decimals, Sometimes there's a lot of problems where there's a solid 0 1s, but yeah, that's kind of the main takeaway. Remember, this one gets cut in half. Only this one, the one you're cutting in half in this case, okay? What's another assumption? You got to remember to get the actual values, and then that force will have to be plugged in here. You got to remember that. If you put negative 20,000 here, that's gonna mess you up. Remember, you can't add the matrices unless they share the same common multiple outside, 10 to the 7 on every single one. What's another one? Trigonometry, right? You need to know trigonometry to find your lengths. Boundary conditions. So there's another important assumption. These become rollers right here. That's because we're assuming there is no displacement in the x, and I've told you, it's like in other problems we've seen that there is, but it's just like very, very small. I think I said 1/3 of a millimeter. And yeah, that is negligible. So it's safe to assume these are rollers, and that gives you 2 boundary conditions. I'm assuming the problem is still solvable, right? You'll have 7 equations, 7 unknowns if you don't do this, but I guess that's a bigger headache. I don't know. Don't take my word for that. I haven't tried it. I don't want to try it if you don't have to, you know what I'm saying? Yeah, there's a 2D stiffness matrix for elements and beams, right? The beams. And I think that's pretty much it. Oh, and node direction. So we went from 1 to 2. So we start at 1, 2. And then we get the angle from 1 to 2, assuming, and you always place the axis on your smallest node. So in this case, it went up this angle. In this case, it went this angle. In this case, from 2 to 4, it went this angle. You see what I'm saying? So always remember, go from smallest to biggest node and then get that angle, and you'll be all right.